Welcome back to my channel. Today is the third class of an operational amplifier or op-amp. Today I will discuss what is the inner circuit of an op-amp or which type of circuit used in integrated of operational amplifier. So without any time waste, let's start our class. So this is the inner circuit of an op-amp circuit, that is the double input double output circuit. Okay, this is the circuit diagram of double input double output circuit of an op-amp. Here we use two transistors. One is Q1 and the another one is Q2 transistor. Q1 and Q2 both transistor are identical and both transistor are NPN transistor, right? This is the base terminal, this is the collector terminal, and this is the emitter terminal of Q1 transistor. For Q2 transistor, this is the emitter terminal, this is the base terminal, and this is the collector terminal, right? So these two emitter terminal is connected with a wire, and one common emitter resistor is connected with the negative supply voltage, that is the RE voltage. RE resistor is connected with the minus VEE point. Okay, this is the collector terminal of Q1 transistor and this is the collector terminal of Q2 transistor. This Q1 transistor is Q1 transistor collector terminal is connect through RC resistor, and this Q2 transistor collector terminal is also connect through a RC resistor. RC is the collector resistor. Okay, and this is also a common point where we connect positive VCC supply. From here we get the V output terminal. From collector terminal of Q1 and Q2 we get the output voltage or the output terminal. Here we consider this is the positive terminal and this is the negative terminal of output voltage. So this is the inner circuit of an op-amp where we use two identical NPN transistor. The two base voltage, that means the Q1, this is the base terminal of Q1 transistor. Here we applied one voltage which is called V1. This is the base terminal of Q2 transistor. Here we applied another voltage. This is named as V2, and this two emitter terminal is connected through a common resistor, that is RE with a minus VE point, and this two collector terminal of Q1 and Q2 transistor is also connected through RC resistor or the collector resistor with the point positive VCC. From the collector terminal of Q1 and Q2 we get the output voltage, right? So this is the circuit diagram. Now what we get if we applied same voltage at the base of V1, at the base of transistor Q1 and the base of transistor Q2, that means V1 and V2. What is the output if we applied equal voltage? If we applied equal voltage, then the output voltage must be 0. Okay. First, next condition, when we applied V1 voltage is greater than V2 voltage, that means V1 greater than V2 voltage, then what happen? From this terminal what we get, when V1 increases, the emitter current of the left transistor increases. This increase the voltage at the top of RE, equivalent to decreasing the VBE of the right transistor. Less VBE on the right transistor means less collector current produced here, right? Less VB of the right transistor means less collector current in this transistor, which increase the output voltage. An increase in V1 produce an increase in V out. This right? This is why V1 input voltage is called non-inverting input terminal. Okay. So when we applied V1 greater than V2, an output voltage with the same polarity we show from the output terminal. That means V1 is called the inverting input, non-inverting input terminal. Third condition, when V1 less than V2, that means V2 greater than V1, then what will be happen? If V2 increases, this will increase the collector current in the right transistor, which means the output voltage will decrease. This is why the V2 input voltage is called the inverting terminal. So this is the logic of a inner circuit of an op-amp. When equal voltage are applied, that means when V1 and V2 is equal, we get zero output voltage. When V1 is greater than V2, we get the same polarity output. That means V1 is the non-inverting terminal and V2 is the inverting terminal. When V1 is less than V2, that means V2 greater than V1, then we get the opposite polarity output. That means then V2 is the inverting terminal, right? So this is the double input, double output circuit of an op-amp. Next, this is the modified version of an inner circuit of an op-amp, that is double input, single output circuit. This is the circuit diagram where we also use two identical NPN transistor Q1 and Q2. This emitter terminal and this emitter terminal is connected through a resistor RE with minus VEE. Here we applied one resistor in the base terminal of Q1 and one signal voltage in the base terminal of Q1. Next, here we also one base voltage that is Vs2 and one base resistor that is Rs2 in the Q2. Here this is the collector terminal of Q1. Here we not connected any resistor, but in this terminal we connect one resistor that is RC resistor, that is the collector resistor, and here we connect positive VCC. This is the modified version of an op-amp. So from here we get the output, that is V out. V out equal to VCC minus ICRC. V out equal to VCC minus ICRC. Why V out equal to VCC minus ICRC? V out equal to the voltage difference of VCC. This is the positive voltage supply minus ICRC. That means what will be the current through this transistor, through this collector terminal, through RC resistor. The current is IC of the right transistor and through which we get the collector current, that is RC resistor. That's why we get here ICRC. That means VCC minus ICRC equal to V out. So when we applied Vs1 increases, that means the emitter current of the left transistor increases. This increases the voltage at the top of the RE, okay, which is equivalent to decreasing the VBE of the right transistor. This is the VBE voltage of the right transistor. less VB on the right transistor means less collector current in this transistor, which increases the output voltage. That means if ICRC is decreases, VCC is increases. Okay, that means Vout is also increases. An increase in V1 produce an increase in Vout. That's why V1 is called the non-inverting input terminal. Okay. On the other hand, suppose input Vs2 increases. Thus, when Vs2 will increase, that means the collector current of the right transistor is also increases. That means ICRC is increases. If ICRC is increases, then Vout will be decreases. That means we get here a negative output, opposite polarity output. That's why V2 or the Vs2 is called the inverting input terminal. Okay. So this is the logic. Vout equal to VCC minus ICRC. When we applied Vs1 greater than Vs2, the right transistor collector current will be decreases. And if this collector current is decreases, that means ICRC portion is decreases, then VCC will be increases. That means Vout will be increases, VCC minus ICRC. Here ICRC, if ICRC will be decreases, then Vout will be increases, and that's why we called Vs1 is the non-inverting input terminal. And when we applied Vs2 greater than Vs1, then ICRC increases. If ICRC increases, that means collector terminal of the right transistor is increases, then Vout will be decreases. That means here we get the negative polarity or the opposite polarity. That's why Vs2 terminal is called the inverting input terminal. So this is the modified version, and this circuit is named as double input single output circuit. Okay. Hope you understand this topic. Thank you. Thank you. If you like, share and subscribe my channel.